Here's an example of where the implied volatilities are not perfectly the same. First of all, you'll notice that there is, these are volatilities, if we just look at the options expiring on 12/18/2004. So we fix the expiration date. You'll notice that the implied volatility has a pattern as a function of the strike price. Okay, no, I'm sorry. Let's go back. So here on this table, we're going to split into the different maturities. So in the first group, you see I've split out the 11/20/2004 maturities, and we see that the implied volatility for the calls, the implied volatility of the 1100 strike is higher than the implied volatility of 1150. You see a definite skew. If you were graphing a volatility as a function of K, it would have this skew shape. It starts off high, and you'll notice that, and drops as the strike goes up. You'll notice that the put volatilities have the same pattern, although not exactly the same. And it's a fair question, why doesn't put-call parity enforce these volatilities? Well, there's a couple of reasons. First of all, put-call parity can only be enforced within trading costs. So if an investor implements an arbitrage, there typically would be some cost, and so these volatilities only have to be close enough to be, in fact, not arbitrageable given costs of trading. But there's another idea that one might observe in the market, and that is that not all of these price quotes will be contemporaneous. That you might find that the price quotes of certain of these expirations, certain of these strikes happen minutes or sometimes even seconds different than the others, and the market is moving quite quickly. So that if you went into arbitrage, you might find that these prices are not available. It was a snapshot in time where all these prices were downloaded, and even though you might in theory be able to arbitrage this vol against that vol, it might be that you cannot trade the put at the 680 and the call at the 3480. And I mean that both in terms of bid versus ask price, but the other point being, if they're not contemporaneous price quotes, one might be stale. You see a similar pattern in the other expiries. Here's they're all skews. Here's a pattern of skews, again declining with strike. Here's a pattern of skews declining with strike. You also notice that volatility for a given strike depends on T. That we go from 1630 for an 1100 strike to 1559 for an 1100 strike a month later, to 1567 for an 1100 strike a month later. So over 3 successive months, a 1 month sigma, a 2 month sigma, and a 3 month sigma, you can see that there is what's called a term structure. So volatility, as you can see in this table, can have a skew, which means it's not, for a given term, it's not constant as a function of strike. Can also have a term structure, which means that for a given strike, the volatility depends on the term. Now, the skew is theoretically inconsistent with Black-Scholes, and the arguments for the skew are that the market does not believe all of the assumptions of the Black-Scholes model in detail. I've discussed a number of them or do not align with observations. And so the volatility skew is a way that the market can introduce adjustments to Black-Scholes prices more consistent with its ability to hedge and make money on the trading of options than one would have directly from Black-Scholes prices with constant volatilities. But again, the term structure, the fact that volatilities depend on T, It's perfectly consistent with Black-Scholes. There's no theoretical inconsistency with that at all.